This presentation is delivered by the Stanford Center for Professional Development.
Today's speaker, Steve Yegge, gave a very nice talk a couple of years ago. So when we found out that he was doing something new, we said, hey, why don't you come back and talk again? Especially since it hadn't received a lot of exposure except for some reason, Microsoft. So this is the second talk outside in the real world. Almost every large software project involves multiple languages, but there isn't a lot of support for systems that have multiple languages beyond, say, make and source control. GROK aims to take a step beyond that. So, Steve.
Thank you, Andy. And just as a process question, we have an hour. Is that about right?
5:30.
5:30. Okay, gives me some time for questions. Okay, hi everyone. Thanks for coming, and thanks for having me here. I'm going to be talking about what I do at work every day, and what I've been doing for the last 4 years. It's a project that I sold and marketed at Google, and they bought it, and eventually it became important, and now it's pretty fundamental to a lot of the planning we do in developer infrastructure, so the tools that people use to build software at Google. There's a lot of uncharted territory here. It's kind of evolving as we go. I'm going to tell you a little bit about the motivations for the project, and then we're going to talk about the technology, talk about some of the future directions, and get your guys' input. So what I noticed at Google and Amazon and GeoWorks and everywhere else I've worked is people like to write tools that process source code for whatever custom reason, whether it's a syntax highlighter or a linter or a transformer of some sort. And they're always reinventing the same wheels. They're like, oh, all right, well, I got to parse the code. I'm going to do a quick and dirty parse of, using the easiest technology available, which is regular expressions. And so if you look at a lot of the code processing tools that are sort of generic, like LXR, the Linux cross-referencer, where you can run them on your code and get some sort of index built out of it, you'll find that under the covers, very often they're using regex matching to try to parse source code. And as we all know, that's not a very good idea. So some of the more sophisticated tools use real parsers, and they brag about it. And they say, we use real parsers to parse the code. And that's much better than regular expressions. But just to put it in perspective, here's the amount of work required to understand source code. And as you can see, these first two here, scanning and parsing, are a very, very, very small amount of the overall work. Once you have a working parser for your code that gives you the tree structure, you've got a long way to go. You've got to do name resolution and type resolution and semantics and data flow and cross-module, et cetera, et cetera. It is lifetimes of work. In fact, it's a lifetime of work per language. So the problem that I set out to solve was make it so that you could get all this and then build whatever tool you wanted to build. Now, what are some examples? So there's some broad categories. IDEs are a big one. We all love our IDEs, right? You get your auto-completion and your jump to definition and class browsing and all that good stuff. Refactoring tools, they do a pretty good job of analyzing the code. They actually fall right about here, 50, 60% of what we're setting out to do. And I'll talk about what the differences are and where we try to exceed the IDE bar, the Eclipse bar, the Visual Studio bar. So that's one category of clients: code browsing, code navigation, code editing. Another category of clients is static analysis. So at Google, when I started this project, we weren't allowed to be a static analysis project because the company didn't think that it was a core competency, even though we hired all these brilliant language and VM and compiler people. But after a couple of incidents involving discovering surprising dependencies that had crept into our multi-hundreds of millions of line code base, with 10,000 well-intentioned engineers hacking away for over a decade, they discovered, we'd find things like the file system depends on ads. Just wrong. And so, they asked why? And they realized they had no idea why, because they couldn't look at the code. And so they looked around and they said, this should really be a core competency for us. You you have a project that looks like static analysis. And so we actually had to go into our design document, marketing doc, where it said GROK is not a static analysis project, and line out not. That's a true story. Now, of course, we had to do static analysis under the covers to get at the information that we wanted to surface, but we had to pitch it as a productivity solution, which to a large extent it still is. So I'm going to show you a slide about some of the sort of categories of users to help you understand who our audience is here in a little bit, but I have a few disclaimer type slides to get out of the way first. It's kind of necessary. So first of all, what is this thing? GROK is pretty vague. There are different ways to look at it. One way to look at it is it is a single canonical structured index of all source code. So in other words, you come up with a standard way to represent artifacts about that code, syntax trees, call graphs, type graphs. We'll talk about all of them. And then you put it in sort of a standardized representation. You have your sort of logical representation, and then you have physical reifications of that representation, maybe in a relational database or maybe in a graph store or whatever. But the general idea is, well, it's sort of like a universal power plug, right? I mean, why can't we have a single universal power adapter that powers all of our machines instead of an Apple one and a Nokia one and a Samsung one? This is basically that kind of effort. This is really best viewed as a standardization effort. Also Emacs. I was accused recently of manipulating my agenda so that I could make Emacs better. And I said, well, yeah, guilty as charged. Because the idea here is that IDEs were designed with the absolute best of early 1980s software engineering practice, and they're completely monolithic. Visual Studio, Eclipse, you name it. These things they're designed with the indexer to run in process with your UI on your local desktop. Everything else is moving to the cloud. Everything. So except IDEs, and they're defiantly non-cloud. They're like fat is good. I've actually heard them say this. So the idea is that we started this project off by saying, okay, IDEs are pretty good indexers. We're going to start with that and work our way up. We're going to just basically saw Eclipse in half, and we're going to run the back end on server farms and then serve it up and see what happens. But then it grew a lot. And what we found was that there are really three primary surfaces that we're marrying together. We're providing sort of a hub and spoke model. Because today, Eclipse is good at Java and okay at C++ and kind of bad at Python and JavaScript and really bad as it goes down. And the same thing goes for Emacs. Emacs is pretty good at C++, not so good at Java, and it goes down. Everybody's got a long tail of languages they do really half-ass support for. Okay? And the reason is that each one of them has to redo all of that analysis, right? The parsing and the semantics analysis until they just give up in exhaustion, and they can basically do indentation at that point. It turns out that a lot of this analysis is very, very, very heavily dependent on the build system that you're using. You really need to feed in the dependencies and the compiler flags and so on to the compilers in order for them to do an adequate job. And that turns out to be kind of a hard problem. But since this is all about standardization, it means that ultimately, although we haven't done it yet, we're going to have to standardize the way that you specify dependencies and other build metadata. But once we're done, you reach this nice sort of ecosystem that people can plug into, and they automatically get all the benefits. So if I have visual slick edit, I like the slick edit editor, say. If it's pluggable, then you can have it talk to our service and decorate files with metadata and do searches and whatever else. And you don't have to reanalyze all the languages. That's the aim. And the goal was to actually put peer pressure on compiler vendors, okay, who have been operating as silos for, ever since we started writing compilers, right? 50, 60 years. And we assumed that they would be sort of uncooperative until it became clear that unless they were playing along, they would have lousy toolchain support. But what actually happened was as soon as they heard about it, they said, sign us up. What data do we have to admit? There's just never been a standard for it before. It's quite nice, actually, quite gratifying. We had to fend them off, in fact, because we weren't ready yet. All right, here's a big disclaimer slide. A couple things, get out of the way. Because people are going to be watching this video, and I don't want to sign up for a bunch of false promises and so on. So this is not a search engine. There are some very good search engines out there. Google internally has a code search engine that's quite good, and hopefully someday we can make that external, but I don't know of any plans for that now. But you can use, free text search or whatever. you have to make this distinction, this important distinction. It's sort of like Google search versus Wikipedia. You go to Google search when you're not quite sure what you're looking for or where it is. And you go to Wikipedia when you know exactly what you're looking for and you want to start browsing edges on that information graph. Okay? So GROK is a graph, and once you have an entry point to it, we have all the data you need. Superclasses, subclasses, callers, call graph, we'll get into it. Getting an entry point into the graph is actually kind of non-trivial today, and we've had to team up with the code search team and with the IDE teams and so on to have common representations of how to name a node. And I'll talk more about it. But we don't do search, and we're not really a client per se. We are strictly a back-end service with some demo clients. But we ultimately expect this to be a marketplace where people contribute 20%, right? Open source type plugins for editors and plugins for compilers and things like that. And there are a bunch of similar projects. One of them was actually, unfortunately, called OpenGROK. And when I started doing the search, the name search, when I started this at Google 4.5 years ago, Google's search engine didn't do stemming on the word grok, even though it's been around since 1968 or 69, stranger in strange land. And so I searched for GROK, and it didn't turn up OpenGROK. Shame. And it didn't do it again last year when I looked. So go figure. Anyway, OpenGROK is kind of a similar product, except that it uses a lot of regular expressions and kind of, whatever matching. But it is a product. It's a thing that you run, and it gives you search, and it gives you browse. And if GROK is successful, OpenGROK will be more successful by being able to use the analysis that we provide. So we're not trying to crush anybody with this. And it's, making it external is this big complicated problem we'll talking about at the very end, but it's sort of a chicken and egg problem. So right now I'm just talking about what we're doing inside of Google. But GROK is different from these things in the sense that we do use real compilers. We made that decision right up front. We're not going to write any compilers. It's a golden rule, okay? Because every compiler is a lifetime of work. It will suck you in and you'll never come out again. Because it's going to be tons of fun, and you're going to be like, oh, we could optimize this, or we could add that feature, or whatever, and then you wind up with GCC, right, or Perl, or whatever, and or Clang. I mean, those people, they disappear. It's a vortex, and all we want to do is like cooperate them without getting too close, because it really is kind of an event horizon. If GROK is successful, ultimately will become a scaling problem, because everybody will be contributing their metadata to us, but that'll become a little bit clearer later. And there have been, in the past, there have been some attempts to do stuff like this, including by billionaire Charles Simeoni from Microsoft, who did intentional programming. And his approach was, we're going to have a structured representation of the code, and you're going to like it. Pretty much, right? And he spent 10 years and however many hundreds of millions of dollars on it, and it was ultimately a miserable failure, as we all know, because, of course, engineers aren't going to like it. They like Emacs or whatever they've been using, right? And so what we do is we try to embrace, we'll index your code even if it's broken. We find people checking stuff in the Google code base, people checking stuff in with merge conflicts that the arrows are still in the file, and we're just like, whoa, what? And whatever, we try to index it. We do our best. So we don't judge your sucky language. That's one of our rules. Trust me, languages don't wear well with one's experience, except maybe C. You get deep enough into the details of any language, and the warts turn into tumors. They're all really, really ugly. It is a lot of fun though to try to figure out when they're the same, when they're sort of ugly in the same way. I'll give you some examples on a few slides, but I already talked about this. Don't write compilers. Sometimes we've broken that rule. Okay, we've contributed parsers, you have to get the compilers like sort of compliant, and that's kind of an effort. It's a bootstrapping effort, right? So we've contributed name resolvers and pieces of compilers, but we really want to, as quickly as possible, get that into the compiler community for that particular language so they own it, because languages evolve, right? There's Java 7 and Java 8 and C++ 11, and there's Python 3, and there's ECMAScript 5, and every single language is in the process of upgrading, its feature set. Sometimes it's syntax, it's grammars. We don't want to have to be in the position of playing catch up all the time. We can't be in that business. It doesn't scale. We ultimately want to handle hundreds of languages and also the cross product. I'll talk about that in a bit too. And then finally, we've discovered that a 90% solution is actually really, really useful in this space. If you're getting auto-completions and they're not 100%, it is, there's no slide for this, but I should probably talk about it before I forget. We have run into a cultural problem where different editor communities have very different expectations about what accuracy means. Okay? Eclipse users are accustomed to waiting potentially infinite amounts of time, but they get perfectly accurate answers. Unless you're using reflection or dynamic loading or whatever, and they go, well, it doesn't really count. Okay, so they've really rationalized and compartmentalized this away. Whatever, anything that's statically reachable by the indexer at the time that you're getting your coffee, because it takes 5 minutes during the autocompletion, is expected to be accurate. Okay, whereas Emacs users, their completion is you open up 250 buffers and you use meta/ to complete against all open buffers and hope that one of them hits, right? It works pretty well, it's kinda. And so Emacs users, if you say, well, we can give you some pretty much more accurate information, auto-completions than you've got now, they're like, all right, sign me up. Whereas Eclipse users say, how could I ever trust any of your data? And unfortunately, when it comes to static analysis, when they're running a big MapReduce over the code and they're saying, I want to find all the calls of this function, and we miss one, they really freak out. So a lot of this is kind of a UX marketing, kind of a trust issue where we really try to get across the notion that you're working with pretty good results here. And if pretty good doesn't do it for you, go write your own. Because this is actually surprisingly grungy. Google's sort of core competency is grungy data sets, and I tell you, our source code, everybody's source code is a real mess. So here's a really high level, super high level look at what our system looks like. Okay, we have source code, including a lot of handwritten source and a lot of generated source, a lot of copy and pasted source as it happens, and we have a set of dependencies, like what are the source files for your project, what are the libraries you depend on, build flags, -d flags, whatever. We send them all to our indexers. The indexers run in parallel in a big batch job every night. And we write them into an index. And then we have an API service that fronts the index, and you can either talk to the API service or you can go against our index directly. You go against the index directly usually if you're writing a MapReduce because you don't want to make RPC calls for a trillion operations. Okay, we'll go into more depth in a bit. Here's actually a different way to look at it. You can look at GROK as sort of a platform stack. So we have our dependencies below the green line here. Somebody has to write the code. That's not us. Somebody has to write compilers or interpreters that are GROK compliant. Again, hopefully not us. The compilers have to provide APIs. In the ideal scenario, a GROK indexer is just a visitor that walks over their intermediate representation. So that means the compiler has to run in a special mode that the compiler is probably not used to running in. Compilers, if you'll recall, their job is to yell at you if you made a mistake the first time. There's no point in the compiler giving you 10,000 error messages because you forgot one semicolon. And so typically what compilers do is they throw away information that they don't need anymore. For example, location information of parse tree nodes and so on. And they barf, they give up at the first error, they balk. And those are two things we need to train the compilers not to do. Because we want to be able to index the code even if it's got a mistake or it's broken or whatever. Moreover, we don't want them to generate any code, usually. Now, ironically, you have to generate code to do name resolution in Java. Java, this is the most backwards, inverted, upside-down logic you've ever heard in your life, but C++ is far easier to index than Java is. Okay? Now, C++ as a language is a real pain in the butt, and if you look at the internals of Clang, it's got a very elaborate representation for all the things that you can express in C++. It's a very powerful expressive language. But for C++, because of the way they do header files, every single one of the symbol dependencies that you need is expressed in your header file, or the compiler doesn't know what it is. It's up to the linker, it's up to somebody else downstream to figure out where that thing is really defined. Which means that all you need to analyze a particular source file is it and the translation unit, the transitive closure, the header files that it includes, and then the command line flags, and you're done. Whereas with Java, it may have to crack open arbitrary directories full of jar files, class files, go off and look in the constant pools and the heads of the class files to find names and look them up, and it has to check the whole class path for this, and it can be very slow, and it's also lossy. They don't record all the information we need about positions and stuff in the third-party libraries. So Java actually turns out to be kind of a pain because you have to do some amount of code generation just to analyze it. And then the build systems, of course, give you no API. What's the API to make? Well, you write your own parser for make files. You know, it doesn't have some sort of programmatic interface that you can use. Well, maybe it does today. I don't know. Maybe GNU Make does. Anyway, at some point we feed it all the analyzers. We stuff it into a persistence layer. And then we either can do queries against it. We'll talk about those. We have an API service for like O of 1 lookups, you know, that people do all the time for IDs. And then this is for interactive support. Hopefully this will be a little bit clearer after we look at the graph and stuff. Okay, this is interesting. This is important. User tiers. We've identified sort of this pattern, which is that 10,000 engineers at Google use GROK every single day to jump to definitions of symbols, to do hover documentation, really simple stuff. File outlines, call graph browsing, just finding their way around. I mean, you jump into a company with 100 million lines of code and no grep, and you need some help navigating around, right? Then you have sort of these power users. Every team's got one, right? Somebody who writes scripts to automate workflows for the team. Team has to do some sort of hairy transformation because some other team didn't provide the right API for them or whatever, and so they write scripts. And so we have a GROK command line tool for scripters where they can make calls to our index and get edges, get nodes, get metadata, file decorations, whatever, to make it nice for scripters. And then you have analysts who want to do SQL queries. Like we have a team at Google who is responsible for open sourcing big hunks of our Java code. The Google Java collections libraries, for example, and so on. And they want to do things like find out what the most popular APIs are. They want to find out how people are using their code. They want to find out who's calling it and from where. So they make extensive use of our SQL interface. We dump it into a column.io relational database. And they make extensive use of our command line tool. And then you've got a few people. We're down to like 10 people now. This is an order of magnitude shrinkage. But they have an order of magnitude more leverage to enable productivity for others. And then we've got like the very bottom level of people who are doing massive code health refactorings and cleanups on our code base. And we know them by name. Tom and Kevin. And it's like they're our friends. Because they can do stuff that makes life better for everybody at the company. Okay, so a couple quick screenshots that'll be completely illegible on this screen, but just to show that, yeah, we really do have clients. So we have this web client that was sort of a proof of concept that we did that looks kind of like a read-only Eclipse. And, it's kind of useful. As you can see, it has a search box. So I kind of lied about not having a search engine, but all it really does is pretty much partial file name match. So it's for looking up files. And then from there, you can say, oh, I have this node labeled statement here. I want to see who uses it. And if you actually click that show cross-references, so here it says we can see the derived classes and we can see the instantiations of this class. I clicked on a class called labeled statement, or we can jump to its definition. So I clicked show cross-references and it gave me this. So it's just like LXR. This is the simplest possible use case for our index, which is find me all the places this thing was referenced. So that's kind of boring, but you got to do it. And we have an Emacs client that does exactly the same thing. So here it is in Emacs. When you open a file in Emacs at Google, it automatically goes and makes an asynchronous call off to our service to see if we know anything about that file. And if we do, it'll decorate the file with underlines and error messages and whatever other interesting stuff we found. Here's a screenshot of the help for our command line tool. I was kind of hard pressed to find any queries that weren't big and ugly. But we do have one. And it's growing into basically what amounts to a shell. It's a shell for basically browsing our index. It's going to be kind of cool, actually, when it's really evolved. We also have SQL queries. This is a real SQL query against our index, against that class that we were looking at just now. It's a JavaScript class. And as you can see, what we've asked for here is edge names. So I'll talk about nodes and edges on our graph and how we represent source code and how the challenges and trials of trying to figure out whether final is the same as const, stuff like that. But in the meantime, you can see that, you know, this class has these edges. It has 138 methods that are declared. So it's kind of a lot, but it is a parser, so it's probably a bunch of recursive descent grammar productions. And it has some usages of the class. Maybe I better show you the graph so that makes more sense here. So here's our graph. Our very small graph, it looks like. This is kind of unreadable, but I'll talk you through it. So this is a very small snippet of source code. It's a hello world in C, and then the signature, the only function that we actually call from hello world, which is printf. Okay? This generates a much bigger graph than this. This is a very tiny cross-section. What we find is that there's about 100x expansion in terms of, you know, file size to metadata size, you know, give or take. And one reason is that we have to come up with nodes in the graph for all the types. So the built-in types, the composed types, pointer types, parameterized types, any sort of type representation at all. It doesn't matter how crazy it is, right? Haskell union types and you name it. It's got to be modelable in our system. And another big set of subgraph of this is the declarations of symbols, user-defined types or functions or whatever. We have references. We create nodes for every reference. So every time you name something, it has a node. And we have nodes for files. Pretty much anything that we would want to represent in the index gets a node, and its relationships get edges. And it's bidirectional. It's an unweighted bidirectional graph. Every edge has a mirrored edge. So if I return a foo, then I can go to foo and say, who returns you? And follow the opposite direction edge, which is quite useful sometimes. So that's the basic idea, right? You start with a graph, and then that's your big hammer, and everything looks like a nail. And we'll talk about what we can do with that graph in a bit. Here's the things that we store in the graph. We store a symbol table, and a type graph, and a call graph, and the build dependency graph. There's a lot of graphs kind of overlaid in this thing. File system structure, generated code. We're working on storing ASTs. I have a slide about that. ASTs are pretty boring, huh? Just parse the code, get a tree. My compiler's prof in college at the University of Washington started off with a statement that parsing was a completely solved problem. It was boring and nobody was looking at it anymore. And boy, oh boy, was he ever wrong. We have found some really interesting parsing problems. I mean, when you get into multi-language, of course, it gets pretty crazy. But even the representation of the parsed code is, everybody has a different idea of what it means, so we'll talk about it. So here's what an actual node definition, I mean, this is the information we store on our nodes. You know, I'm not trying to hide it or anything. Every node has a globally unique identifier. Globally unique-ish. Okay, why is it ish? Okay, so we found, for starters, you know, like there are a lot of names that I'm going to talk about this more in the naming problem, but we find that versions and sort of copies kind of introduce hairiness into the whole model. Like we have like 2 complete copies of the Java JDK sources for completely different reasons somewhere in our depots. And so if somebody is making a reference to JavaLang object, it could be either of those or neither of those. And generating a unique identifier for them sort of involves having to put more provenance information in there, like about which depot it's in and so on. So we keep thinking that it's unique, and then somebody will pop up with an edge case that actually turns out to be non-unique. So we've decided recently, basically, that all nodes should really be node sets that are usually singleton sets, but all clients should be set up to expect in advance that any query that's really exacting and precise could potentially give them back 2 matches or more matches that are all like, did you mean this? And we have a display name to show the user what it looks like. We have display names for like local variables. Like there's no syntax in a language for anything that you can't address. You can't get the address of a local variable in somebody's function or a parameter, right? You know, or a catch block tag or something. But we need to be able to address it in GROK because you may need to be able to make a link to it. Or you may just need to be able to create a reference to it temporarily when you're refactoring so that you can come back to it later and move it and say, oh yeah, this thing, is it still there? So GROK synthesizes names for everything. We make them up. We have our own syntax. We found over time that that evolved into a query language. What happens is if you have a method and it's overloaded on parameters, so like Java util arrays.sort, you know, has like 80 overloads because of the type explosion, because Java was, well, all languages suck, let's put it that way. But for a variety of reasons, they have lots and lots and lots of overloads. And so if you say, I want to go to Java util arrays sort, or I call Java util arrays sort, potentially what you're doing is a wildcard match. You want to get all of them back, like if you're auto-completing, say. And so what we have to do is introduce, support for partial qualified names, and then for fully qualified ones. Now in C++, the full qualification for a particular name of like a template instantiation can be pages and pages and pages long. We found signatures from Clang that were 64K strings. Okay, it was astonishing. It looks like a mangled name, but no, that's actually the declaration that you would type in by hand for this thing if you were fool enough to have to do that. So what we try to do is come up with a prettified name. And this is kind of an open area for us where we're really struggling with it. But basically we've recognized that there's kind of a correspondence between name and URI. And we really want a sort of a RESTful view of this whole index. And it's also kind of a query language. So I don't know. I don't have a lot to tell you about that today because we're still working it out. But it's definitely an interesting problem. The biggest thing to look at here really is location. This is going to come back and bite us again and again, slide after slide. Location. All code has to have a location, and most of it doesn't have a location. But we'll get to that. Yeah, here's a big long list of node kinds to prove that we have different node kinds. You don't have to read it all, but basically we represent all the things in the code, right? Kind of grouped roughly by category. There's type nodes, there's function nodes, there's number nodes, and we try to be. So here's the thing, right? Is you can get really, 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 really precise for no reason at all because nobody cares about the distinction. They just want to know it returns a number. They want to know it returns a signed int, but they don't care what the precision is, maybe, right? So GROK has been this sort of constant sort of evolution of increasing precision, right? Finer and finer grained modeling on demand. So we come up with a new client that says, well, I need to know the difference between a lexical closure that's writable and not writable. And we say, oh, well, OK. We go back and we fix our model. But we did see that there was some value in coming up with this is an enum, basically an enumeration of all the possible roles that a node can have. This is really complicated, but this works pretty well. And that's been our general goal, is to try to do something that's reasonable for our users and then iterate on it. And here's what the edges look like, okay? We went back and forth on edges, and we eventually wound with this. We wound up, because every edge is an arrow. And you know the classic problem where everybody draws their inheritance arrows differently. Some schools say, I inherit from this class. And some people say, I inherit from this class, right? And that actually matters, like when you're composing a syntax where people actually have to type out an arrow in the query to say what they're looking for. So you gotta kind of canonicalize these things. And so what we came up with was the convention that the node always extends from me to you, right? So I extend you, and I am extended by you. Or sorry, you are extended by me is actually the way it works. So each one of these is by and large verb and verbed by. It's not always the case because we don't want to have this incredible proliferation of edges. We like to reuse wherever possible because we want to be cross-language, which I'll talk about in a little bit. So we have a couple of cases where we reuse edges because they're kind of close. Again, we fuzz the semantics a bit. And so we wind up with, for example, base type, composing type, and type parameter are kind of a triangle that we use sort of liberally when we're doing parameterized types. Anyway, the details aren't really important. Just to know we have around 100 node kinds and around 100 edge kinds. And each new language that we add adds how many new node and edge kinds? Well, fewer and fewer and fewer and fewer until eventually someday it's going to be none. Now, we've met with a lot of internal resistance to this idea of having a cross-language representation for. And part of it is that compiler writers, and actually anybody who's like really a zealot or an advocate of their language, they feel that their language is a special snowflake and nobody else's could possibly be as complicated or as interesting as theirs. They all think this. You know, we have not to date ever found a feature that did not exist in at least 2 languages. Now think about that. Think about the craziest language feature that, you know, the most out there, you know, the C preprocessor. I mean, come on. How many languages is that going to be in? Well, it turns out it's used extensively in Mozilla's JavaScript code base. So, you know, there is nothing that you can say is uniquely yours. Everybody has the same, you know, like, you know, Lisp symbols, you know, Ruby stole it, so Ruby has symbols too. You know, I mean, it doesn't matter what feature. So, yes?
Come from?
Come from. So we have, that's kind of a rat hole. There are a few cases where we know that there are languages coming where we're only aware of one, okay? But it's almost always possible for somebody to come along and come up with a counterexample and say, well, you know, that's a Lisp feature, but it's in Dylan, or that's a Smalltalk feature, but it's in Squeak, you know, and they can make a distinction that you can say, well, those are really kind of the same language, and they say, no, they're not, and it depends who you're talking to, because they may have different runtimes or whatever. So intercal, probably. At this point, I'm so jaded, okay, that probably even brainfuck has like a derivative, right? Brainfuck prime. I know the guy that wrote that language, by the way. Okay, so anyway, in any case, what we do is we don't assume anymore that a language feature is unique. But the big question that really people want to know, they say, if they think about this really hard and see where we're going, they say, are you writing a compiler? Am I going to be able to write a compiler that goes against your intermediate representation and compiles code? Are you going to have that rich of a semantic representation? And if so, how can it possibly be language neutral? Because those two are at odds, because my language is special. And, you know, the answer, I think, in the fullness of time is that yes, eventually, you know, there's no reason why we wouldn't have that much information and more. We have all kinds of stuff that we collect from linkers and loaders and so on, runtime even, the compilers don't have any access to at all. You might even be able to write a better compiler against RIR. It does mean that we are providing basically a union or a superset operation over all these language features, and sometimes the union is one, okay, come from, maybe, fine, okay, and so we'll have one special edge in there just for that language, but that's not really the problem. The problem is conflicts. The problem is when we've modeled two things as the same and they're not really the same. So if this is the last sort of major sort of entity we have in our graph. We have nodes. We have edges, and nodes have modifiers. Modifiers are bits of metadata that are composable, right? You can basically OR them together. They're flags. And these really are, this is a dumping ground. This has really become the dumping ground for language semantics, right? Pretty much if you capture scope, you know, and structure and, you know, the call graph and the types and stuff, at that point, this is just flavor, right? This is just your particular language's curry seasoning or MSG or whatever. And so, well, I'll go through some examples later, but there are subtle differences between a lot of these things that look initially the same, and we argue endlessly over whether they should be the same. For example, const, final, immutable, unmodifiable, and read-only. Are they all the same? Okay. Well, we know that const isn't the same because const is actually basically a wrapper type in C++. It's a type that provides basically a read-only interface around the constant thing. You can cast it away by going around it. So const is definitely out. But the others, you know, the semantics are a little weird. I mean, if you think back to what Java's final means, first of all, it means two things. And so one decision that we made early on was whenever a language has a keyword or a modifier that means two things, we're going to split it into two modifiers. So final means you can't subclass it or you can't override it. It actually means three things, depending on whether it's on a class or a method. Or if it's on a variable, it means you can't write it once it's been initialized. So we split those into, you know, non-subclassable, and I don't remember, I'll have to look here. Now I'm curious. Terminal, I think, is what we eventually called classes that you can't subclass. And we have immutable for things that are write-only. But in Java, you know, there's this really subtle language edge case where if you have a final variable and I compile against it, it's a constant, say, you know, static final int x equals foo, and I compile against it, then what I get is a copy of foo. So even if they did change it, say through runtime reflection or whatever, or they just changed it and recompiled it and I didn't recompile. Now we're talking about two different copies of foo. That's a subtlety that matters to compilers, that matters to runtime, and we don't capture it at all in our view currently of, we just say, yeah, you can't write it, you see? So, each one of these things, we wind up having to go through all the languages we know, and so I hired a bunch of people who know a lot of languages, and, and we refine it as needed, but we try not to get too refined. Because if you over-model it, then it's just wasted work if you're never going to have a client who cares. In fact, you can do some damage by saying, okay, well, we have ints and floats and big nums and complexes, and they're just like, I just want to know if it's a number. And so basically, you have the clients now having to back into ad hoc polymorphism over all of your finely modeled types, because what they really want is when it behaves like a thing. So anyway, public, global, default, exported, they all mean kind of different things. Built-in, extern, pre-declared, implicit, auto-generated, all kind of the same, all mean different things, etc. So what we do is, we do our best. And we make them the same. We split them out when we need to. Okay, let's talk cross-language. Cross-language. How do languages call each other? Does anybody ever write in one language? Of course not. Never, ever. Not for anything significant. So you can call via foreign function interfaces, Python calling into C++, say. You can call through RPCs, obviously, Java calling a Python server, say. You can, embedded languages, World of Warcraft, Lua, you write all your scripts and it's calling down into C. Language embedding also, probably the canonical use case, if you're not into World of Warcraft, would be JavaScript in browsers, also pretty big. And they have, if you look at JavaScript, it's a true scripting language. Not like Perl or Python or Ruby where it's just a dynamic language that tried to be everything for everybody. No, JavaScript is a scripting language in the sense that they've clearly defined an interface by which it's expected to talk to an underlying runtime and basically allow you to compose and call the entities like, for example, your DOM and your CSS representation and your browser frame windows and so on, right? So, we want to be able to trace from a JavaScript call down into the DOM or from a JavaScript call over AJAX to your Java server. I mean, of course we do. Everybody wants that. IDEs don't do it today, but there's absolutely no reason we couldn't figure that out if it's at all statically decidable, or if we can even cheat. I'll get to the cheating slide in a bit. And of course, yeah, there's code gen is huge. My God, everybody uses so much code gen. Especially Java people, but everybody, but especially Java people. They use a lot of code generation because Java is fundamentally incapable of expressing, a whole bunch of things that other languages have no problem at all with. And so Java people like to write declarative things in XML or in whatever and then compile it down to Java. And so half of all Java code is generated code, that some transformers spit out. Transformers are even peskier than compilers. Compilers sometimes will record position information for you from where stuff came from so that you can jump back to it, right? Transformers are usually somebody's hack, right? Somebody wrote a hack and they're, oh yeah, we're going to make JSON out of this, and so it's a Perl script. And then they left the company and it's been running like that for years, and you're like, hey, we want to update your Perl script to get GROK metadata information. And it's pretty hard. It can be pretty hard. Code generation is a big problem for us, but we're doing a pretty good job with it, I would say. Anyway, the overall point here is that there's a gazillion ways that languages can talk to each other, and it would be kind of foolish for us to try to train our indexer about all of them, like hardwiring it. It would be better if we had sort of a clearinghouse for saying, okay, here's a way, and it's a tricky problem, okay? Okay, so let's take Mozilla Rhino. It's a JavaScript implementation on the Java VM. It's used in Google Apps Script. It's used in all kinds of applications. It's JavaScript, it's server-side JavaScript that runs on the Java VM. It compiles down to Java bytecode. You can make any Java call from JavaScript syntax, basically, but it has a JavaScript, runtime there too. And you want to call into a Java bean or something. Let's say, actually, Rhino is powerful enough to let you declare Java classes. Jython can do this too. You can actually create a class that can be called from Java, okay? And so now what's happening is you're introducing a cross-language binding. The thing that's analyzing the JavaScript or the Python side has to say, okay, I'm introducing a binding over on the Java side. So yeah, what's your guys' naming convention for that because they're completely different across languages. So we have to solve this problem of basically allowing languages to sort of inject information into each other, and it's something that we made sort of significant progress on, but it is distinctly non-trivial. So the next like 5 or 6 slides are just going to be problem after problem after problem that we've run into, and it's just been kind of a miserable slog. And the only thing that keeps us going really is that our customers love it. Now they express their love by saying, "Your index sucks and it's driving us nuts." And they say, "Why is this template expansion not taking me to the right place?" And we're just like, right? But it's tough love, but we know they love it because they're using it, right? So default, okay, so the location problem, okay? You want to jump to the definition of something. You want to see it as a cross-reference, right? Somebody's calling you. How do you show it if it has no location? That includes things like default constructors, implicit, items that are generated, anything in a macro expansion. JavaScript. When you write function foo in JavaScript, actually 3 things are created, right? Your function, the function constructor object, which is also a function, and the function prototype object, which I believe is also a function. Although I don't think they get their own prototypes and constructors. I'll have to reread the spec. But in any case, at least 3 things are created at that declaration site. So today, what we do is we say, it's kind of there. I know you didn't really say there's a prototype here. You could have said it, but you didn't. So right now we use some sort of hacks. And there are certain situations where there's a reference to a file, but not to a particular location in a file. Classic example, an import. I'm importing this file, in Python or whatever. So where's the location of that? Well, it's kind of the whole file, sort of. And so we've kind of had to work out these conventions where, there are different kinds of locations. Some locations are a span, starts here, ends here. Some locations are a whole file, some are like a nothing, right? It's like right here between these 2 characters. Some locations are, what's the location of void in C? Okay? Well, the location, we've decided, is the canonical documentation on whatever website we trust the most. So the location is a URI. We do that for all the built-ins. And then we have languages that have operator overloading. Will let you overload the array bracketing operator. And then when you actually use it, what's the location of the reference? Is it the first bracket, or is it the last bracket? Is it the whole thing? Or do you just shoot yourself because it's a lot easier? So it's the first bracket, as it turns out. I don't know, we just made something up. So this is kind of hard, but we need to generate locations for things. I mean, yeah, when you get into lexical closures, there's kind of there's a scope there. We know it's there. The location is this runtime thing, right? But we need static locations for everything. So location, big problem. And what we do is we make them up. Naming. You need to be able to name stuff, right? Like anonymous functions, which by definition have no name. And yet we have to name them. And so what we do is we name them $1 and $2 and whatever, right? We give them names. Local variables don't have names that are visible to the rest of your program, but we invented our own little syntax. So it's foo.bar ampersand some local variable, right? Eventually, we need to be able to name AST constructs like try and catch and switch blocks, and because people need to be able to query on that stuff. Imagine, if you will, she looks skeptical, which is why I'm clarifying here. Imagine legal needs to do a query to find out anytime somebody called a function with the word Mozilla in it in a loop. That's the thing. They need to know if somebody called anything with Mozilla in it in a loop. You don't care what language it is. You don't care what the destination was. It just had the string Mozilla, and it had to be in some sort of loop. Okay? Well, that's a pretty language neutral query at that point, right? You need to be able to have some way to say in a loop in the query. And so being able to name AST structures, and we're not the first to do this. We've seen a lot of cases where people have come up with sort of ad hoc tree pattern matching or pattern query languages for ASTs, and they're all useful, in their own way, except when you add the preprocessor in, and then they're completely not useful, but it's a complicated problem. Anyway, we make up names for stuff. We have to come up with names across languages. So here's a big one, right? Is everybody is always calling, they're always calling or using an identifier in some other language that somebody else is going to figure out. But they're talking about it in a doc comment. And they're like, okay, what's going to happen here is there's going to be a code generator, and it's going to generate this .h file, and then that's going to get linked into this program. So C, and there's no way to link to it because there's no such thing as cross-language linking. Java doc lets you link inside of Java. Doxygen lets you link inside of C++, right? PyDoc, JS doc. every single language thinks of itself as the only language in the world. They're like professors, right? And so, you know, they're like, yeah, nobody else matters except my class. What we have to do is we have to come across and we have to say, all right, well, basically GROK : //, right? Come up with a URI syntax that all languages can share. We're not there yet, but we're getting there. The aliasing problem, yeah. So the aliasing problem is you have a name that really is a reference to some other name. C++ reference parameters, Python import foo as bar. So I imported foo, but I renamed it. And that's kind of a problem, right? Because like if somebody says, well, I want to find every place where somebody used foo, you have to include all the bars too. So what you could do is you could just say, oh, yeah, that's the same thing, and not capture the fact that there's an alias there, which works until somebody says, I want to find out everywhere somebody used an alias of foo. And then they're like, oh, well, you can't throw any information away if they potentially need that. So you actually have to have a node bar and a node foo, and you have to have two things. You have to have an edge between them that says, oh, yes, there's an alias here. And you have to automatically flatten or join those when people are doing the query where they don't want to distinguish the two, right? And so in other words, your single edge lookup, O of 1, really guaranteed. It's going to come back in 3 milliseconds, no matter rain or shine. Now all of a sudden is an arbitrary walk of declarations and declals and aliases and whatever, and it's hairy. But, well, we got to do it. We're like the post office. We got to deliver it. The syntax tree problem. Okay, yeah, ASTs, easy, right? Easy. No. So we found early on that everybody was using the word AST or syntax tree or parse tree or whatever, and they all meant different things. It was like they're walking around and they had these little thought bubbles, and they all had completely different scribbles in the bubbles. Some people meant they just wanted a tree. Like these guys were doing this binary tree diff algorithm on code reviews where they were trying to narrow down the part of your file where you had broken somebody's build. And all they needed was a tree structured representation. They didn't care about the language or the names or anything. They just wanted to be able to like do basically binary division on code blocks. They really wanted a tree. And then most other groups come along and they say, well, what good's a tree if I can't look up the name and the type of the name and the symbol table and, you know, the type table, right? So they want, you know, basically a full intermediate representation, a decorated tree, an annotated tree that's gone through maybe semantic analysis and tells you whether there are error nodes in there, right? Or variables that have been used before they're assigned, you know, definitely, or whatever. And then you get, like, compilers will lower the tree as they go, right? They start off with some source and they'll make a tree, but they'll be like, you know, this thing's eventually going to turn into a jump, so I'm not even going to represent it as a loop. I'm just going to create a jump label and generate the partial bytecode for that thing right now, okay? Which screws us, right? Because now we've lost, we no longer have a faithful representation of the original source code. So one of the reasons that we go in and we contribute parsers is we have to go in and we have to add a separate code path for toolchain mode that doesn't do any of that no-no stuff like pre-lowering, which messes up the performance. Like it's lose-lose, because now we either have two separate parsers, which is a maintenance problem, or we have two separate code paths, which is still potentially a performance problem and a source of bugs, or we have one code path that has a lot of ifs in it. We haven't come up with a good solution for this, and yet tools are so important. I mean, why did I do this project? I did this project really because engineers, smart engineers, a lot of engineers from Stanford, okay, because they just go next door to Google, were coming in and they were making language decisions not based on the merits of the language, but as it turns out, on the merits of the tool chain. And that turns out to be sort of the status quo. Engineers make their default choices about, you know, what they're going to be comfortable doing something in based on the quality of the tools and the type of tools that they're used to using. I thought, well, that's kind of stupid. What if this language is way better than that language for this particular task? And the answer was they don't care. And so if we could find a way to make, you know, sort of the same universal high-quality tool support for all these languages, then in theory, okay, some engineers might try to choose a different language. Hopefully. I mean, it's not really that hard at that point. I mean, the biggest argument against bringing a new language into a company, they say, oh, well, it's scary. What if somebody looked at something and couldn't figure out what it did? Well, you know, at first I was like, well, you're stupid. And then, you know, over the years I tempered that to be, I see, this is a tools problem, okay? You shouldn't have to figure out what it does. It should tell you what it does, which I think is a bit more moderate. See, so, you know, my old age, I'm getting a little bit less grumpy. Now I get mad at the languages themselves, because I'm like, why aren't you telling me what you're doing? Okay, so then we have, where are we? Oh, yeah. Do you include comments in a syntax tree? No, because they're not part of the syntax. They get stripped out before the parser even sees it, right? except everybody needs it. What if you're using the syntax tree for refactoring and you want to move something around? You want to carry the comments in that locale with it, right? In the vicinity. Same thing with keywords. Nobody ever stores keywords. It's like, why would we store keyword nodes with a location and a span and all this metadata about it when it's a keyword? And the answer is, well, same thing, right? Refactoring, code navigation, code understanding. So we wind up having to store a lot more information. It's a huge pain in the butt. Mixed language becomes an even huger pain. I have some really clever stuff that I can't talk about in this space. Sadly, my team's not letting me. But maybe I'll come back in a year and I'll be able to talk about that. Mixed language is going to get really interesting. Okay, the opacity problem. Yeah, this one's cool. So what I noticed as I was writing these analyzers is that frequently there would be information available, it'd be right there, and it's like, hey, am I allowed to use that? Like, for example, somebody's making a query inside of a string, and I know statically, like the system that they're querying, right? They're passing they're passing a SQL query through a JDBC API, say, right? Or they're importing something, but the language syntax dictates that you put the import inside of a string. And so the parser, Go does this, right? So the parser comes, or actually C++, you can use a string or a literal, right? A symbol. So, sometimes the parser will give you back and say, oh yes, this is a string. Move along now, right? And we're like, but wait, right? We know the context here. We could be actually going in there and figuring out what's in that string and what does it mean. What if it's a regular expression literal? It's like, well, we have access to maybe to the regex parser. It has its own tree representation. What if we could give the user the ability to navigate inside the regex? I mean, for regexes, that could actually be pretty useful for some pretty hairy ones, right? So we find all these situations where we can actually look at data that it's inherently noisy. It's messy, right? It may be malformed, it may be incomplete, it may not be there in all source files, and yet, another good place is comments. It's a basic question, it's a UI question. Should your editor underline a name of an identifier in a comment? Okay, so I've got a class fooBarbaz, and I'm using fooBarbaz all over the place in my code, and I mention fooBarbaz in a comment. And I hover over it. Should I be able to see it? Or is the comment private? You know what I mean? Is it opaque? Is it quoted so I shouldn't be looking in there? And the thing is, if you try to do what I think is the right thing and actually underline the name, then you start getting into heuristic land. Because what if the identifier is there, T-H-E-R-E, right? And they say, oh, well, hello there. And they're not really talking about there, but you underline it. It's like those horrible ad schemes that just look for just random, text matches, and you're reading an article and they're saying, oh, you're looking for the, here, click on this, right? It's horrible, right? It's a horrible experience. And so, your heuristics start to get kind of fancy about what counts as a potentially resolvable name inside of a comment. But we do it and people love it. And they're like, woo, it's so smart, except when it's not. And then they say, I hate you, but it's love. Okay, the linking problem. Oh yeah, the linking problem. We use real compilers, we brag. We thought we were so cool. Turns out compilers suck, right? Compilers punt on everything. Compilers only care about compiling a particular translation unit, one class file, one .a file or .o file, right? I mean, their job, or one bytecode snippet. And compilers are critically dependent on the inputs, like the preprocessor, and more importantly, later phases like the linker and the loader. And those things do a lot of the name resolution, where the compiler's just like punt, right? And so we ask the compiler, so what is this thing? And the compiler's like, That's the official answer from the Clang team or whatever. And so then we got to go to the linker team and say, yeah, we need to make your linker GROK compliant, right? And they're like, oh yeah, no, we can do a good job with that, except for, oh yeah, this is a DLL. You're going to have to ask the runtime for that. And we're like, it just goes on forever, right? People like defer stuff lazily. And so, this is a problem. GROK has to play the role of preprocessor and compiler and linker and loader and, at some point, this is metrics. We're giving people metrics on their code. And metrics beget metrics. You got me on my metrics rant. Nobody can look at a metric or a graph or a chart without wanting more, right? They're like, oh, that's an interesting, why, right? And they make you go back to the drawing board. It doesn't matter until you can watch ants walking around on the loading docks, right? They're like, where did that ant come from? So the thing is, we're going to run into this situation. People are like, well, you do a really good job with static analysis, but have you looked at the log data? And we're like, yeah, we'll get there. So GROK really has to be, really has to understand everything about the code that's available eventually. Okay, oh, we're almost on the last slide, which is good because we have time for questions. So analysis and queries. I finished this slide like right before. So we're starting to do queries, like real-for-real queries, right? Not just lookups, but analysis. Now, we can give people the index, and we could say, go write a MapReduce and go wild and figure out whatever you want about the code, which is just like a restaurant saying, here's a cow and a knife and a plate, go make your own steak, right? It's no fun. Nobody's going to do it. It's messy. And so what we want to do is we want to try to find a sweet spot. I'm going to have to use a new metaphor because I think I just killed her with that one. So we're going to have to find the sweet spot where casual users who don't want to learn a bunch of stuff can do reasonably rich and sophisticated queries on the code. And they come to us all the time with these queries. I mean, every single day somebody's mailing me and going, hey, Steve, what's the syntax for saying, OK, I want to find all the methods that return HTTP servlet request. And I go, oh, yeah, that's easy. That's just a single edge. Yeah, that's one lookup. And they go, or any subclass of HTTP servlet request. And I'm like, OK, because that's a graph walk. That's a graph expansion. What we found, OK, first off, we started kind of cloning Eclipse and LXR and some of these older tools. And we would do cross-references. And I showed you cross-references. And I said, oh, yes, everyone knows cross-references, right? What we found is that cross-references are a canned, predefined query of sort of generic blandness that's kind of minimally appealing to everybody, but not very satisfying to anybody. And what people always want to do is they want to add filters. They want to say, well, yeah, I want to see all these results, but only for my project, or only for their project, right? Or only for files that end in, foo. And then they want to and then they want to take that set of nodes and they want to follow an edge, and then probably more filters and follow another edge, and they basically are doing this expand, contract, lather, rinse, repeat. It's XPath, basically, right? This is exactly what XPath does for XML documents, right? You select a node set, you have a moving cursor. As it interprets your query, your XPath query, it's keeping track of the current node set, and it gives you not one, not two, but 13 different dimensions that you can go on from that node. You can say follow all the ancestors, all my siblings, all my next siblings, my descendants, my children, my namespaces, my attributes, whatever. It's a horrible, horrible mess, right? Well, when we looked at ours, we have like 100 different dimensions that you could potentially want to go in. It's all the edges that we have, right? I showed you the list earlier. So it's actually potentially quite a bit more complicated than XPath. The thing is, we're looking for a sweet spot here. We don't want a manual this thick. I want something that is roughly as hard to learn or as easy to learn as regular expressions or XPath. A tool that everybody can learn once, get out the manual if they have to do something really fancy, but for basic queries, it's pretty easy, right? And I want it to go and and I don't want it to be able to answer every question in the world, but I want it to be able to do some reasonably rich queries because people need it. People need it. So, I have no idea how to do it. I really have no idea. I mean, we're just starting on this. We do know how to interpret it. We know that Google has some really, really nifty graph computation engines that we can shove our graph into, and they can tell us spanning trees and clicks and clustering and all kinds of cool stuff. So this is all uncharted territory. Obviously, you can use Datalog and SQL and whatever. We do use SQL today. The problem with SQL is it can't express recursive joins. And that's what people are really doing with this graph walk. They're saying, OK, join all that to this, and join all that to this, and then filter, select where, select where. And since you can't do recursive join in SQL, your only option if you want to offer people to reduce the number of joins necessary for a given query is to denormalize, which Google does a lot of. Google's like, what? Full table scan? Why do a full table scan when you can look at every single row in parallel at the same time? Right? So that's how our Dremel SQL index works. Or they'll say, why walk the edges when you can just store the transitive closure? That blows up really fast. But if you narrow it to the really common queries, and so let's say, take an example. I want my superclass chain. Multiple inheritance, that means potentially it's a big DAG that goes up, right? So you could have them walk potentially 10, 12, 15, however deep your class hierarchy is, levels, to fetch that data. Or you could just, from every class, store a link called ancestor to everybody in its DAG of its superclass chain, its ancestor chain. It's wasteful, it's piggish, it's expensive, it's horrible, right? But it's awfully convenient when you do that SQL query and just go, give me the ancestors, right? So, it's always, as usual, a space-time trade-off. That's where we're at today. So, a little bit of scaling, yeah, we've got kind of a scaling issue. I suspect that Google's code base is nowhere near as big as Microsoft's or Amazon's. But we do have 10,000 diligent engineers cranking out code, and everybody measures the code base size every once in a while, and they all come up with radically different numbers. I mean, these numbers are, I might as well just be making them up. I mean, it's really weird. You would think, especially since we have a single tree, more or less, that you could just look at it and see how much code is in there, but on any given day, it'll vary just dramatically. And people are like, what? Why are there 20,000 fewer JavaScript files today? And just nobody knows. I mean, we really don't know. I mean, it would take forever to go figure it out, and you figure it out and go, oh. And then it wasn't worth the time, right? So it's kind of a mystery at this point. I'd love to turn GROK into a metrics package that can tell people all about how big and hairy our code base is. But right now, basically, it's more of our enemy than our friend, right? We have to run analyzers over all of our code all day long. And what's more, users aren't happy with yesterday's data. They want to know the data that's up to date with their typing. You just added a function. You want to be able to find all the callers of that function you just wrote. And so we need to be able to write, we need to be able to sort interactive, which we're working on. There's some tricky problems with mixing your local data with the global data, right? If you delete a function, we can't just go, oh, okay, well, I don't see it here, so we'll go look in the global index, because you deleted it. We actually have to put in a deletion token, right? All the standard stuff. This actually turns into a garbage collection problem when you look at it closely enough. When you look at incremental indexing over time. But that's the goal, is we want to actually store all the revision history for all the code. Every time somebody does a change, any change, we want to just basically layer it onto the graph with versions, and then you can do historical queries, and people will love it, except when it doesn't work, and then they'll hate us. But that's tough love. And then we have all these other challenges. A big, long list. A big, long list. Other depots, other languages, other build systems, other clients, incremental indexing, interactive, canonicalizing ASTs, so that, they can be the same across languages, except when they can't be. Standardizing all these protocols, et cetera, et cetera. It goes on forever. This project will take forever. So, what do we do? Well, we try to, use other people's work as much as possible. Now, a lot of people have come to us and said, how can I help? And the answer is, well, we're not actually pushing most of this stuff out open source yet, because it's kind of not ready. We're embarrassed to show it. It's buggy. If our own engineers are complaining about it, we hardly want the whole world complaining about it. However, you can prep, okay, you and anybody watching this video and anybody interested in this space at all, can prep by going in, and we can even publish a doc about this. We have an internal document that says what a compiler has to spit out to be GROK compliant. Because it doesn't matter if your format's exactly the same as ours, right? We can write a visitor that walks it and gets the info we need, as long as you're providing it. And so, if you happen to be working with a language community or a compiler or an interpreter or a code generator or transformer or anything that spits out code or processes code and spits out, stuff, then you should probably take a look at the document that I'm no doubt going to have to publish that says, here's what we look for. It's pretty basic. We want an AST that represents the code with location information for everything. And we want a symbol table, and we want to be able to look up types. And if you're calling it as some third-party package, we want to get all the information for that thing too, right? And don't throw anything away. Expose it all. It's not too hard. You can contribute to open source, compilers. You can write your own type inferencer. We do dynamic languages too. We have a great type inferencer for JavaScript. We're working on a great type inferencer for Python. They do outstanding jobs. It's almost as if you're writing Java code or C++ code. You can hardly tell that it's a dynamic language. Go in and do it for Ruby, so that it'll be easy for us to GROK Ruby, or Lisp or whatever. Or if you're in the editor space, if you're in the toolchain space, if you use Vim or Emacs or Eclipse or IntelliJ or any extensible editor, go in there and if you ever get an urge, work with them to split it up and modularize it so that we can be the index. So that they can be a thin client that does a nice presentation of the index, but doesn't need to do the analysis. We can do it in the cloud. All right, that's it. Questions? Talk you all out. Yes?
Would you look at searching how the code is used? Like if someone searches for a loop, would you return instances of tail recursion?
Yeah, so we would actually, yeah. So that would have to be language specific, right? If it were scheme, or if it were, say, Clojure, we would have to actually specify to the user. We would model tail recursive constructs differently from loops, even though the compiler is just going to compile it down to a loop, right? So now that said, Okay, that's specifically for the use cases we have today. But we've had a lot of customers come in and say, well, we want to do security analysis using your representation, which implies that we need to store, the, data flow graphs and control flow graphs and so on, right? So, which means single assignment, basic block representation, where it really is just a loop, right? It's just a jump target. And so, down at that level, they really don't care whether it's tail call optimization, or it's a loop or what, right? Go to, they don't care. So a lot of it depends on the client and whether they need to know or not. Other questions? Yes?
Did you finally get to use Common Lisp inside Google?
Did I personally finally get to use Common Lisp inside Google? No, not yet. We did purchase ITA, which is a fantastic flight reservation system that was written largely in Common Lisp. And so it has become a semi-quasi-blessed language in Google as long as you don't use it. It's complicated. Politics are always complicated. But there's sort of support for it. You can actually use it to talk to Google infrastructure. Now, whether you have the guts to use it and not get death threats from your colleagues, well, I got a death threat for using Scala at one point. It was a half-joking death threat, so it was like half a death. At that point, I was like, I just don't think I'm going to use it. Down the road, I hope so. And the way that we're going to do it is we're going to write a GROK analyzer for Lisp that makes the tools just as good as they are for Java today, which is a really painful thing to say for anybody who's got a Lisp background, right? Because there was a day when Lisp had the best tools in Smalltalk. It will come again. Any other questions? Yes?
You showed a lot of stuff with static analysis. Have you given some thought to more dynamic analysis?
Okay, yes. So we've talked a lot about static analysis. Have we thought about doing any more dynamic analysis? And the answer is, yeah, about as much as that. I mean, we have some people who are doing different kinds of dynamic analysis. Obviously, we've got some JIT teams, some VM teams that are doing, JIT tracing and that kind of thing. We haven't really talked to them much yet. We've really got to kind of nail the static side of it first. It would be kind of I don't know. I mean, there are a lot of different directions that we can go. We can go off and chase them. And for a while we did, because we were looking for low-hanging fruit, easy victories. But then eventually we realized that we had this giant sparse feature matrix, and what we really needed to do, now that people were using it, was really fill in some of those sub-matrices so that people would trust us. And I would rather nail the trust on the static before we do dynamic than do a half-assed job at both. Someday. Other questions? Yes?
So there's another, you had compiler flags on your list of things. There's another whole space out there, like what version of the compiler is doing this?
Yeah.
And what OS is this package running on?
Yeah. So the question is, I said, oh yeah, compiler flags, as if there's only one compiler for the language and one operating system is the target. When in reality, there are multiple compilers, especially for C++, right? There's multiple compilers, there's multiple systems, system header files you could be bringing in. Yeah, I mean, analyzing Windows code is actually a little bit different from analyzing Mac code or Linux code, And this actually shows up in the AST representation thing, right? Because different compilers have different ASTs for everything, right? I mean, the way they represent a method might be completely different, Often compilers will translate them down into a child-sibling relationship tree, so they can quickly just iterate over the tree. But if they do any sort of rich modeling, they may come up with different representations, we found. Like Java-C's representation of Java is different from Eclipse's representation of Java. Clang's is different from significantly different from GCC's. And what happens is, as soon as you start exposing ASTs to people, you've made a contract with them, right? They don't want to have to go, you don't want to break their code if you switch back-end compilers, which we've done now twice, at least twice. We switched from the Eclipse CDT indexer to Clang, once Clang started really kicking ass, and we switched from the Eclipse Java indexer to Java-C once it became clear that that wasn't going to die. And anybody who was using our ASTs at that point had to be rewritten. So now we have this kind of open question: do we come up with a language neutral, not a cross-language canonical, but at least a compiler neutral representation of not just that, but the types, and for C++, you can get into how you represent templates and instantiations and specializations and things like that. It's tricky. And you can throw into the mix the build system. You can be using the same compiler and the same OS, and you can be using Ant or Make or Maven or Google's build system or whatever, your own build system, and Yeah, so this is a problem. This is a problem where we're getting into views of the graph that are kind of specific to your project. And so we want to introduce the notion of a project space in our graph, so we can keep track of what version of the compiler was it, what tool chain. You know, we use a cross compiler at Google that can, in theory, use GCC or Clang, because we use them both actually. So now we've got this basically hypervisor of a compiler that we got to talk to. It's quite complicated. And the answer is, like for most things, we punt right now. We don't do a very good job with that. What we're offering people is a service where they can use they can run their own version of GROK on their own branch, using their own compilers and tools and stuff. And the index that's produced will be all the things that are relevant for their workspace, which is a compromise, right? It's not perfect. We'd like to be able to, you know, generalize across these things and come up with a generic representation for what the compiler flags are needed are, the include path or whatever. But we'll get there. Might be years, but. We understand the complexity of it, and what we do is try to make the maximum number of people happy for the minimum effort at each step. Does that answer your question?
Yeah, that was interesting, but it wasn't what I was trying to ask.
Okay.
Suppose I've got a specific compiler, and I switch from version, 13.2.6 to 13.2.7 because it fixes a bug.
Right. Yeah, no, that problem also, the problem of compiler versions fixing a bug, which potentially could change the representation of the code that we've stored, is generalizable across. It actually happens the most with our build system. Our Blaze representation changes, every few months, and if we're storing historical versions, now we've got fundamentally different semantic representations across versions, and it makes querying hard. Like you have this question of, okay, from 13.2.7 to 13.2.5, there was this change in the way these types were represented. Do we backfill the data so that today's queries are as if we had been compiling a code with 13.2.7 all along? Or do we tell clients, okay, at this particular point in time, your query is going to get kind of weird, right? Is that closer to the problem that you were asking about? Yeah, and this is a problem. It's even a problem if the compilers don't change, but our data model changes. Our representation becomes more accurate or more precise or whatever to fix a bug in our representation. And this is actually a common problem with anybody who's representing historical data at Google, right? I mean, even if it's maps data, right? If you start collecting different data, do you go back and retrofit all the old historical maps if you're keeping it around? And boy, oh boy, I don't know. Do you know? God, I'd love to know the answer to this.
Track of what was going
yes,
on at the right time.
You're right. You have to keep track. You have to model the change itself. That's ideally, right? Yeah, boy. So that's a kind of a meta modeling.
And you have to be able to recreate the environment.
Yep. Yeah. So we have run into this problem a few times. The need to sort of we want to. So it's not related to GROK, but we have a source control system, and people can check in code, and at a particular point in time, the code might be good. And then it's bad for a while as people make changes. And people may want to go back and they want to get a fresh build, even just for QA purposes of that particular time. But unfortunately, the Blaze, the build system, our build compiler, as it were, has changed dramatically in the meantime. So you have to go back and you have to be able to check out the compiler at that point in time that was used. Yeah, it's pretty hairy. I mean, it's hard, when you come to Google, it takes a while to realize how much storage space we have. We have a lot of storage space, and you need to start thinking in terms of storing everything for all time, even if it seems wasteful. And we're getting better about that. I mean, it was only maybe after 4 years on this project, just over the holidays here, that I realized that we could probably store our metadata for every file save that everybody does all the time for all history. And I was like, oh yeah, I did the math, and I was like, oh yeah, that's a tiny data set. It seemed huge at first, right? So yeah, will we model those changes? Oh God, yeah, eventually, maybe, but that's hard. That's hard.
One of the tricks that hardware guys often do is when they finally get a board or a chip done, is they take the PC that they've been doing the work on.
Yes.
They just unplug it and hopefully put it away there in case they ever have to come back to it.
Yeah. So what we'll do is we'll make a copy of our data center every time we produce an index. Yeah. Okay. So you got me. That's a hard one. We haven't done that one yet.
Beige box in the corner.
Any other questions? Any easy questions? Yes?
How do you represent like macros and that sort of thing in your graph? I mean, what is a macro?
Lisp has sort of tree macros, and it also has reader macros, which are like lexical. So it depends whether you're talking about basically
Let's
tree
just say
macros.
C preprocessing.
But text macros, they're a little tricky. We're working on them like this quarter. What we want is really obvious. Okay, we want to be able to click on a macro and see it's one level expansion, and potentially it's n level expansions. And if there are any, so if there are any macros used within the macro expansion, we want to be able to expand those and so on, right? And then if there are identifiers that are created or referenced inside of the macro expansion or its recursive expansion, then we want to be able to index those things. We have some clever ideas that my team won't let me talk about, but I will definitely lump that in the hard question category. It's definitely not an easy space. I mean, I think Brian Kernighan, or maybe it was Dennis Ritchie, said a couple of years ago that, yeah, if they had to do it all over again, they probably would have left the C preprocessor out because it just made such a mess for tool chains forever after. But then it wouldn't have been successful. So it's tough, right? All right, well, thank you. You've been a lovely audience. Thanks.